Alright, this is Mr. Gilm, and today we're learning more about congruent triangles, but more than that, we're actually going to start proving that triangles are congruent. So just a reminder, to be congruent, it has to be only in rigid motion. They must have the same exact angles, same exact sizes on the segments of the angle. So in this case, specifically, we're looking at triangles to see if they're congruent. So there will be 3 equal angles and 3 equal sides. Now the third angles theorem basically says if 2 triangles have 2 of the same exact angles, then that means their third angle must also be exactly the same. And if you really think about this, it's almost like common sense. And it doesn't matter if I put in like, let's see here, what would be a good number to put in here? 75 degrees, and I put in, oh, I don't know, 50 degrees for this guy. If this angle is also 75 degrees, and this angle is always 50 degrees, we don't know the relationship between A and L, but I can tell you every single time, no matter what, if 2 angles match, the amount left over for the 180 degrees is always going to match as well. So in this case, if we have 125 degrees between our 2 angles and we need 180 for our triangle, that leaves 55 degrees for A. And that would be the same exact equation for angle L. That would have to equal 180 degrees. So at the end of the day, basically this theorem, this common sense theorem almost, says that if you have 2 of the exact angles in each triangle, then the third angle must also be exactly the same. Okay, so 50 and 75, 50, 75. Okay, 2 of them are congruent. That means there's only that much left for the last angle in either of the triangles. So call it the third angles theorem. So just remembering the name of it more than just the common sense part is going to be important. The third angles theorem. So as I'm writing this 2-column proof here, basically what I want to do in this chapter is to prove that 2 triangles are congruent. So in order to do that, I need to make sure that I have proved that there are 3 segments that are of equal value, congruent, and there's 3 angles in each triangle that are exactly congruent. So that's what I'm going to go for. And they've done a lot of the work for me. They're giving me quite a bit of information here as far as segments and angles are concerned. And what we're going for is triangle DEF is congruent to GEF. So we're trying to make sure that DEF is congruent to GEF. And so the congruent and the valid congruent statement needs to actually work as well. So we need to be careful with that. But let's start with the given. And what I'm going to do is I'm actually going to break this proof into 2 parts. We need to make sure there's 3 equal segments, and we also need to make sure there's 3 equal angles, or congruent angles, I should say. So I'm going to start with just the segments. I know that DE is congruent to GE, and I also know that DF is congruent to GF. Now that's all I know about the segments, just these 2 pieces of information. And I need to make sure that the last remaining segments are congruent. So as I'm looking over here, I know that they're giving me that these guys are equal and these guys are equal. But the nice thing about it is it appears that these triangles actually share a side. And so these properties that we have taken for granted for so long, like the reflexive, the symmetric, the transit property, 1, 2, 3 RST, they are actually going to be really handy for this, because if this shares a side EF, or if DEF has a side EF and GEF has a triangle side of EF, then we know that if they share a side, we can prove that EF is congruent to EF through the reflexive property. It's just saying that they share a side, and EF is always going to equal EF because they're the same. Okay, so we're going to call that the reflexive property. And we're going to put a special name with it today. We're going to call it the reflexive property of congruence, since we're not dealing with equal signs. All right, and of course this was the given. And so now I have all 3 segments proven that they are equal. Okay, not so bad. Now we got to go with the angles. So it tells me that angle D is congruent to angle G, and that's just a given information. And it also says that angle DFE is congruent to angle GFE. So the angles that we know for sure that are equal are this guy, and where's his congruent angle at? It's really hard to see in this picture, but It looks like it got pixelated. Those two are equal. And it says DFE, this guy, and GFE are equal. Okay, just put a little dash on them so we know they're equal. So we just need to make sure that DEF and GEF are equal as well. Luckily, we just learned a theorem for that. And of course, this is the given. This is given information to us right here in the beginning. We just learned that if triangles share two exact angles, then their third angle must also be exactly the same. So we're going to say that angle DEF, the last angle that we haven't compared, must be equal to angle GEF. All right, and we're going to call that the third angles theorem. All right. And so finally, if we have proven that we have three segments that are equal in a triangle, or congruent in a triangle, and three angles that are congruent, three sets of angles that are congruent in a triangle, then I know for sure that the two triangles must be congruent. Triangle DEF is congruent to triangle GEF. And as for reasoning there, we're going to say the definition of congruent polygons. Okay, if all the sides are the same and all the angles are the same, then therefore, through definition, they are congruent. They are the same. Okay. Let's take a look at the next one here. And once again, I'm writing a two-column proof, and this time my diagram looks a little different. This is a little trickier. Once again, we have some given information here, and we're trying to prove actually that two triangles are congruent. So we need to make sure that we have all three segments proven equal and all three angles are proven equal. So let's look at J and P. So it tells me the angle J and angle P, and we can go with the angles first this time if you want. And ooh, that's the only angle that they give me. So we better go with the, ooh, there's a whole bunch of good information in this thing. Okay, so for the given, let's go ahead and let's start with angles. And you know what, since there's so much information, let's just knock all the given out at once. Angle J is congruent to angle P. JK is congruent to PM. JL is congruent to PL. And L bisects KM. Okay, that's just, I literally just wrote this whole given cloud over again. All right, so that's all the information that we know. And the approach I'm going to take here is I know that angle JKL or JLK is congruent to angle PLM. All right, this I know. JLK and PLM are congruent. This guy is congruent to this guy. And this is a theorem that we've talked about before in the past. Angle, we're going to call it JLK, is congruent to angle PLM. And we just took a test on this actually. Those types of angles where they share a vertex are called vertical angles. So we're going to call it the, we're just going to say vertical angles are congruent. That's just what we're going to say. The definition of vertical angles will be fine as well. So now we got two of the angles knocked out, and we need to make sure that we have a third angle that is exactly the same. So what I'm going to say is angle K must be congruent to angle M, because we have one angle, two angles that are congruent, and the third angle theorem tells us that if two of the angles are congruent, then the third angle must be congruent as well. I'm going to say the third angle theorem. All right, so I'm going to say, okay, we have, they're given, the J and the P. We know that these are vertical angles, and we know through the third angle theorem that if that's all that's left over for both of them, it's going to be the same amount through the third angle theorem. So now we got to just mess with these segments. So JK and PM, that relationship, as well as JL and PL. We got 2 out of the 3 already. We just need to make sure that the last segment is congruent. So we got that guy and that guy, that guy and that guy. So what we need to do is we make sure that segment KL is congruent to segment LM. And if I go back to my given, L bisects KM. And so basically what you need to do for your proof is you just need to say that if it truly bisects, then each side is equal. So we're just going to say the definition of segment bisector. That is what a segment bisector does. It cuts a segment into 2 pieces, 2 equal pieces. Now that we have 3 equal angles, boom, 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 and we have 3 equal segments, 1, 2, and 3. Put a little segment sign up there. Then I know for sure that these triangles must be congruent. So I know that triangle JLK is congruent to triangle PLM. And what we're going to do is we're going to use this little abbreviation. And it is CPCTC. CPCTC. Corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. And CPCTC. It's a tongue twister for you. All right, and just finally, I just want to remind you of 1, 2, 3 RST. Works with congruencies too, as far as triangles go. And triangle ABC is congruent to ABC. That's the reflexive property. Okay, it's congruent to itself. The symmetric property says if I have triangle ABC and triangle EFG, if I rearrange the triangles in order of congruence and put EFG first and ABC second, they are still congruent, just because I wrote them in a different order. And the transitive property finally says, with 3 congruent signs, 1, 2, 3 RST, if ABC equals EFG and EFG equals JKL, then ABC and JKL must be congruent as well. All right, so just a reminder on the reflexive symmetric transitive properties. We're going to come back to those more later when we do additional proofs, but that's it for today.